Hello everyone, in this video we will design a distributed job manager or task manager. This is a pretty common industry problem. If we can design a generic job manager, we can use that to solve many different problems. Let's think about a restaurant job manager. What type of requests we get? In a restaurant job manager, we can get like make pizza request, make burger request or make pasta request, right? Whenever we receive a job request, the job manager basically creates a job in the notebook or like database. And each job has a job ID, job type, then a status and some job data. Once jobs are stored in the database or notebook, we have some worker who will be kind of pulling them out of the job DB and start working for them. When a job is done, the worker will again update the job status into the database, and later if customer wants to know the status of their job, they can call the job manager and job manager will return the updated status from database. Similar way, let's think about a different type of job manager. Say for example, delivery job manager. Say we are providing a solutions for delivery, and we have different customers like DoorDash is requesting us for a delivery task. Uber Eats and Instacart is also creating jobs through us, right? And our delivery job manager will store all the job requests into the same database, right? Every job has a job ID, type, status, and some data. Then similar way, we have some worker who works as kind of like delivery job finisher. They pull some job from the database and start working for them. Whenever the job is done or the job moves from one stage to another, the worker updates the same database. And again, if customer wants to know what is their job status, they call our job manager and job manager reads the latest status from our database and return to customer. And using similar pattern, we can solve many different job manager or task manager type problems. Let's try to define our service first. So if we think about the very simplest form, we have customer. Customer will be calling our front end service, and front end service will pass the request to backend, and backend will do the actual job here, right? If we think from the high level, what are the APIs we want to offer? To keep it pretty simple, we will offer two different APIs. One is create job API, another is describe job API. In the create job API, we will get like customer ID who is asking for the job and what type of job they are requesting and some job info. These are the request parameters. And similarly, for the describe job API, if customer give us the job ID, we already know the customer ID, right? So customer ID and the job ID, then we can return the latest job status to the customer. What will be our backend service? I am not talking much about front end service because it is just straightforward routes the request to our backend service. So when we will do our actual backend service design, in the sync path, we basically stores the job information into our database for the create job API. And the actual job creation happens in the async path. We will talk a little bit late. And another API is describe job API. When customer calls the describe job API, our job manager reads the latest job status from database and returns to caller. And what happens in the async path? In the asynchronous path, we will have multiple workers who will do the actual job and update the job status in our database. Let's try to design the high level architecture of our whole solution. We need actually multiple instances of our front-end service because we are thinking a large scale solution where we will be receiving a lot of customer requests. Say for example, we are launching 3 different services or 3 different instances of our front-end service. Then we obviously need a load balancer which we can place in front of our service, and that should be an internet facing load balancer as our customer will talk to that load balancer. Now in our backend, we basically need a lot of instances of our backend services. The reason is the solution we are designing, it's a resource intensive solution. We need to do a lot of work. That's why we need multiple instances of our backend service, and each backend service will have multiple hosts. So for the communication of our front end to backend, we can also put an internal load balancer in front of our backend services, and only our front end service will be able to talk to our internal load balancer. And whenever backend accepts the request, it does some processing on the jobs and stores them in the database. Then from our async path, we also do the actual job. Now, what is the most complex part here? The complex part is what happens when a request lands on backend. We need to understand that part. That's why in today's lecture, we will be focusing only on that part, because other things are pretty straightforward and simple, and like other solutions, we won't kind of waste our time discussing all the topics. So we will go straight into our backend. Let's dive deep into the backend design. The first thing we need to understand is leasing. So we have multiple jobs, right? Say for example, many customer is requesting and asking for doing some job, though they are similar types of jobs, right? And we have multiple hosts in our backend. For this type of scenario where we have multiple job requests coming and we are storing them or queuing them somewhere, and we have multiple hosts who will be actually executing the job, we need a mechanism like which host will do which job. And for this kind of assigning, we use the concept of leasing. So what is leasing? Leasing is basically a concept of like virtual space or virtual bucketing, and all the jobs are assigned to some leasing or lease space or lease bucket, and these leases are also mapped to some hosts. Say for example, the first 5 jobs are assigned to lease 1 here, and this lease is mapped to host 1. That means these 5 job will be eventually done by host 1. What do we have actually inside the job info? So for each job, we have a job ID, we have a job status, and we have some job data, right? And what do we have for the lease info? For this lease, we have a lease ID, and we also store the owner host ID. That means who is owning this lease, or which host actually owns this lease. And we also another value last renewed at. We will talk about this a little bit late. We need that for renewing our leasing purposes. And we also maintain a mapping of our job ID versus lease ID here. So every host actually knows which leases they own. Say for example, here we have 10 different hosts. Host 1 knows out of these 10 leases which are owned by host 1, and similarly host 2 knows which leases are owned by host 2. And if one host goes down, its leases will be free and be occupied by other hosts. Before going into the full solution, we need to answer some questions. The first question is, does the job ID to lease ID mapping change? The answer is no. Whenever these jobs are created for the first time, they are assigned some lease ID, and this lease ID map does not change. The reason is we have fixed number of leases. Say for example, we have 100 leases and it's predefined. Whenever a job is created, it gets a random lease ID, and that ID never changes. The next question is, does the lease ID to host ID mapping sense? The answer is yes. It's pretty obvious, right? The host can go down anytime. If a host goes down, those leases will be free and picked up by other hosts. That's why the lease ID to host ID mapping can change. Now let's answer some good questions. Say for example, who creates the job and who assigns the job to a specific lease. For these, we will be designing a job manager who will be responsible for creating the job and assigning the job to the lease. The next set of questions are who assigns the leases to a specific host, also who decides when and how to redistribute the leases. To answer this question, we will design a lease manager who will be responsible for doing this stuff. So now we have a job manager who creates the job and assigns them to lease, and we have a lease manager who actually assigns the leases to a specific host, and if a host goes down, it also redistributes the leases. Now the next question is when the job are finally mapped to host, how it's executed. So for this we will be designing a job executor which will execute the real job. So we have three main components here: job manager, lease manager, and job executor. Now we will try to dive a little bit more. We will talk about lease manager. Say for example, we have good number of available leases which is fixed. In this case we have 10, right? And we also have hosts. How many hosts do we have? 2 at this scenario. We are saying lease manager runs on every host and it calculates the fair share count. What is fair share count? Fair share count is like how many leases a host can own. And how do we calculate this? Total number of leases divided by total healthy hosts. So total number of leases is 10 and total number of healthy hosts is 2. If we divide it, the answer would be 5. That means our fair share count is 5. Every host can own only 5 leases or at most 5 leases, right? And what does the lease manager do? Lease manager actually iterates over available lease database every 8 seconds, say for example 10 or 15 seconds, and asks for ownership until it receives its fair share. So lease manager goes over these leases one by one and asks for the ownership. If they are free, they will be assigned to the requesting host. How to calculate the available leases, right? To make sure that if a lease is assigned to host 1, it's not again being assigned to host 2. So in our previous slide we talked about like last renewed at, right? So every lease maintains a field called last renewed at. If last renewed at is older than s seconds, it could be like 10 or 15 seconds, that means the owner host failed to renew the lease and it's available for pickup. Say for example, if host 2 goes down, it won't be renewing its leases, and when the time window passes like 10 seconds or 15 seconds, those leases will be available kind of for pickup for other hosts. So we do not explicitly releases the leases, rather if any host fails to renew the lease, those leases will be considered as like available for pickup. Now let's try to answer one more question. What if a host goes down? Say for example our host 2 went down, right? Now we have one host. What will happen? If host 2 goes down, host 2 will fail to renew the leases and all the leases from host 2 will be available for pickup, and at this time everything will be picked up by host 1. So another question, what if a host is added? Say for example we had 2 hosts here, now we added one more host. So technically we have 3 different hosts and total leases are kind of 10. 10 divided by 3 is equal to 3 point something, and we can consider is at 4. So what will happen? The fair share count will go down, right? It was 5, now it went down. So all the hosts will try to renew their leases, but after having at most 4, they won't be able to renew the 5th one. So this one will be available for pickup by the new host. Similar thing will happen for host 2. They won't be kind of renew all the leases, and some of them will be available for pickup by the newly added host. Another question, how to calculate the total healthy hosts? So each host publishes their own health metrics to our observability solution. Technically, every host has a health manager. We will design it, and this health manager will be responsible for publishing the health data to our observability solution as well as our database. We can utilize our observability solution for monitoring and alarming based on various metrics, and also we can store the latest health status of the host into the database from where the lease manager can lease and identify the total healthy hosts. Now let's dive deep into the job creation part. First we will talk about job manager, how a job is mapped to a lease. So the job creation actually happens in the sync path of the job manager. In the sync path of our job manager, we do some input validation and data model translation. If the current host has free leases, job manager selects a random one of them. If the current host does not have any free leases, the job manager selects a random host or leases from any available host. So after creating the job and assigning a lease ID to the job, finally the job manager saves the job into job info database. So technically this is the end of job creation sync path. Now we will dive into the async path part. Say for example, we have a host here. We are taking host 1 as an example, and we also have lease DB and job DB. We have lease information in lease database and job information in job database, which are saved from the sync path of the job manager. So in the async path, we have kind of a scheduled workflow which is running on the host at a fixed interval and loading the leases into memory. What leases it's loading? Only the leases which are owned by this host, not owned by other host. Whenever we have the available leases, the job manager iterates over the lease and load them into our in-memory job queue. We have a pusher which basically does this. It actually reads or iterates over the available leases and selects the jobs where we need to pay attention or execute some task, and only those tasks are pushed into the in-memory job queue. Later we have a puller which pulls the job out of the job queue, and based on the job ID it gets the job metadata and other information from job database. When the puller have all the job information available to it, it basically passes the information to the job executor. Inside the job executor, we have lot of worker thread ready. So this worker actually executes the real job. When the job is done, they notify the puller, hey, we are done with the job. And the puller finally updates the latest job status into the job DB. So this is the complex part of our real job execution. Let's go over it one more time. From the sync path, we store the job information in job database, right? And in the lease DB, we have our kind of lease ownership and other things which were already done by our lease manager. And our job manager async workflow first reads the leases owned by only this host. And then the next step, we have a pusher who is iterates over these leases and selects the job which needs attention and push them into the in-memory job queue. There we have a puller in step 4. It basically reads the job out of the queue, and using the job ID, puller also pulls the job metadata from job database. When the puller has all the job information, it notifies the job executor to execute the job. This job executor basically knows what to do based on the job type, and it notifies a worker, hey, execute this job. When worker finishes executing it, the job executor again notifies the puller we are done with the job. And finally, the puller updates the latest status of the job into the job database at step 9. Let's try to zoom in into the job executor section. So our job executor is basically the concept of Java job executor or Java thread pool executor. What is a thread? Thread is basically a single unit of execution, right? So for example, whenever we execute a program, we actually creates a new thread. Say for example, every Java main method or function actually creates a new thread. So in our case, we need to do a lot of work, right? Say for example, we are getting thousands of job requests which are being executed simultaneously. So if we want to create these thousands of like worker threads or Java threads every seconds, so managing, like creating the thread, managing it and closing it are kind of resource intensive, right? It actually slows down our process. So that's why Java introduced a concept of thread pool. Thread pool are basically managed collection of pre-created threads which are ready to execute tasks. If we use this thread pool to execute our job, then we can save a lot of resources for not like kind of creating and managing threads. That's why we use the concept of executor. Our job executor has some other custom support also. The job executor basically knows what to do based on the job type. And whenever the job executor receives a request, it basically knows where to send it. So we have multiple thread pools created. Say for example, one thread pool for pizza, another thread pool for burger, something like this. Whenever the job executor receives a job request, it basically throws the job into the respective thread pool, and if any worker thread is available, they will do the job. When the job is done, again the job executor will notify back through some callback mechanism, hey, we are done. Finally, let's try to summarize the whole thing. We have customer is calling our front end service, and front end service, after doing some authentication, authorization and basic stuff, routing the request to our backend. In our backend, we have job manager. Job manager has like sync path and async path. From the sync path, it basically creates the job and stores it into our database. Then we have lease manager, who is basically kind of iterates over lease and make sure the host has its correct number of leases assigned to it. Then the job manager async path basically reads the leases which are assigned to it, iterating over the leases. It pushes the job into the in-memory job queue. Then we have a puller, who is basically pulls the job request and notifies the job executor to execute them. When the job executor finishes executing the job, it notifies the pusher back, and finally the pusher updates the latest job status into our database. We also have a health manager here at the bottom. The health manager kind of continuously pushing health data into our observability solution and our database store. So that is kind of the whole story. Hope it will help us to design many similar solutions. Thank you.